is broadcasting. So
wonderful. So welcome everyone. This is the third seminar in this series organized by the G5 Commission of the IAU. And today we're pleased to have with us Nikku Madhusudhan. We have also with us Daniela Korkakova, who is the main organizer of this series and who will be also moderating a discussion we'll have at the end on resources for the topic of our talk today, the exoplanetary atmospheres. And we also have with us Katia Cunha, another member of the organizing committee with Daniela, myself, and others, who is gonna briefly introduce Nikku. So I let Katia to go on.
Okay,
Just
good
keep
morning.
your microphones off and your cameras off.
Thanks, Carlos. So good morning, good evening, good afternoon, everyone. So welcome to today's talk, which is organized, as Carlos said, by the IAU Commission G5. I'm Katia Cunha, and it is with great pleasure that I introduce our speaker for today, Dr. Nikku Madhusudhan. Madhu did his PhD at MIT, then he was a postdoctoral fellow at Princeton and Yale, and in 2013, he became a lecturer and then a reader in astrophysics and exoplanetary science at the University of Cambridge. And his talk today will be on exoplanetary atmospheres. Madhu, take it away, please.
Hi, everyone. Thank you very much for inviting me to present this talk. It's great to be here and to share some of the excitement that's happening on the forefront of exoplanetary science. So exoplanetary atmospheres, as you know, is a fast-growing field and known to be the cutting edge of exoplanet science. We are seeing some really exciting developments, over the past several years of new spectroscopic data, new techniques, getting good atmospheric remote sensing information. And in this talk, I would like to share some of that excitement with you. Okay, so this is going to be the outline of my talk. I'll start with just a big picture to lay out the big picture of the field. And then I'll go over a quick semi-review of the area of exoplanetary atmospheres as to what is the quality of observations that we are getting these days. And then most of my talk I'll actually spend on some science directions that are emerging in this field. I'll admit up front, I will not be able to do justice to every single area within exoplanetary atmospheres, but I'll take the liberty to pick a few areas that I think are going to be very dynamic over the next few years, and that I'm particularly excited about. So I'll share some of my personal views towards the end of the talk. And much of the later half of the talk I'll be spending on the emerging sub-Neptune regime, how we know of the majority of the planetary demographics is in the small planet regime, and we are beginning to get atmospheric observations of planets in that regime as well. So I'm going to spend quite some time on some exciting areas there. And then I'll end with future directions. So I hope we'll get a broad brush of the field as well as some details on a few selected topics along the talk. Okay, so this is sort of a big picture slide, that everyone in the field basically has been very well acquainted with for a few years now. Already, this is an old plot from the Kepler mission. This is to just drive home the point that already almost a decade ago, we knew that the exoplanetary demographics are favored hugely towards small planets. Okay, so this is early to 2010s that I'm talking about some of these figures from these ones. So you can see here on the y-axis is the size relative to Earth, and the x-axis is the orbital period. And you'll see these horizontal lines for Earth, Neptune, and Jupiter. So this is where we expect ice giants to be, Uranus and Jupiter around 4 Earth radii. Uranus and Neptune around 4 Earth radii, and Saturn and Jupiter around 10 Earth radii. And already you can see that the planets between Earth and Neptune size dominate the exoplanet population. However, the first planets discovered almost 20 years ago, over 20 years ago now, were not the small planets, obviously, for detection biases. So we detected tons of hot Jupiters in the early phase of the field. And those are also the planets that are most amenable to atmospheric characterization. So we had tons of atmospheric observations for hot Jupiters. So we learned some cool atmospheric physics that way. But if you think of the exoplanet demographics as a whole, those are not the majority of the population. So we are just entering into this lower and lower mass regime in atmospheric observations. But you can already see the demographics here. Again, the distribution, you can see the radii distribution of known exoplanets. This is again with the Kepler mission. So this sort of goes along with the plot on the left that small planets dominate. So if we already know that exoplanets are extremely common, we know of thousands of planets now, and we know that the occurrence rate, is close to 1 planet occurrence rate. It could be anywhere between 50% and 100% per star. Then why are we looking at many more missions, space missions, and ground-based facilities to detect more planets? Of course, the answer for that is that it's very well that we know of the large numbers of planets that exist out there and the high frequency, and that exoplanets are extremely diverse in their bulk properties. But if we want to do anything beyond that, you want to basically have spectroscopic information. In other words, you want to understand the atmospheres of this process, of these planets, observe atmospheres of these planets to understand various physical and chemical mechanisms that are happening therein. Okay, so a broad question that has been around for a good part of the past decade is to ask, how diverse are exoplanetary atmospheres? And in order to answer that broad question, we want to observe many of such planets around nearby stars, nearby bright stars, so then we can characterize their atmospheres. And that is the reason why there are many more planet detection facilities even now and coming up to detect more and more planets around nearby stars. Okay, so brief 101 lecture on atmospheric remote sensing. What exactly are we trying to do when we say we want to study atmospheres? This is just one cartoon of a large range of atmospheric processes that we can already study in exoplanetary atmospheres today. Okay, so this y-axis here is the pressure going down as you go up in the atmosphere, which means this is basically a proxy for height. And then you can see that as a function of height, various atmospheric processes dominate. Okay, very deep in the atmosphere. So I'm also showing some temperature profiles here, a few different types of temperature profiles. The gray line, is a standard profile for an isolated or not very highly irradiated atmosphere, whereas the cyan and red curves are for strongly irradiated atmospheres. One has a thermal inversion, other not. This is just to show that there is a wide variety of temperature profiles you can have in these atmospheres. But one thing that's common in all of this is as you go down to high pressures, the temperatures either become isothermal or increase monotonically. So in the high temperature, high pressure regime, you expect chemical equilibrium processes to dominate because the chemical reaction timescales are very fast, okay, are low. So chemical equilibrium will dominate, and as you go higher and higher up in the atmosphere, various non-equilibrium processes start to play a role. So at the very beginning, you'll have a lot of atmospheric dynamics going on, and then the part of that dynamics is also not just lateral mixing, but also vertical mixing. So you can change the chemical composition of the planet just from that, just by mixing chemical species from the lower atmosphere to the upper atmosphere. You can obviously have clouds, hazes, all sorts of condensation and photochemical effects. And then you can, as I already said, you can have thermal inversions in the atmosphere, like the ozone layer, the stratosphere in our own atmosphere. And then you can have a regime where photochemistry entirely dominates your chemistry, your chemical composition higher up in the atmosphere. So you can see all of these as a function of pressure or height in the atmosphere. And eventually, you'll hit atmospheric escape. That's where species, once they break down due to photochemical destruction, they can escape to space. So these are all processes, but what do we do with them? The only window we have in order to probe all these atmospheres is the electromagnetic spectrum. So we, at the end of the day, we are observing spectra of these planets, and depending on which wavelengths you observe these spectra in, whether you observe them in UV, optical, or infrared, you can probe to different depths in the atmospheres. That's because of the opacity of these different species that dominate different parts of the electromagnetic spectrum. So for example, if you're looking for molecules, you can probe like deeper in the atmosphere in infrared wavelength, and you can go all the way to like the 1 to 0.1 bar atmosphere, where you probe all these molecules, which themselves act as tracers for these various chemical and physical processes in the atmosphere. There are other species like the alkali metals and the heavy metal compounds, which have strong transitions in the optical regime, and those, turns out the tau of one surface in the optical photosphere happens much higher up in the atmosphere. So if you're looking in the optical, that's where you'll probe. And then if you probe in the UV, you see the transitions from these atomic and ionized species very high up in the atmosphere. So I hope you get the big picture here. The principles of atmospheric remote sensing of exoplanets is that depending on which wavelength or frequency you observe your spectrum in, you're probing different chemical species, and those chemical species act as tracers of different atmospheric processes. Okay, so that is what we are up to when we are saying we want to study exoplanetary atmospheres. And once you have put constraints on these chemical species and hence constraints on these various processes, you can do more fundamental studies of the physical processes in these atmospheres using ab initio modeling and so on. So there are numerous planets now for which this is just showing a rough summary of observations, that atmospheric observations that have already been made for exoplanets using the Hubble Space Telescope, transmission spectra, emission spectra, and for several planets using ground-based emission spectra. But what you'll notice, the peculiarity in this plot is that most of the observations are happening in the high mass, high radius regime. So that's what I was saying at the very beginning of the talk, is that the hot Jupiters dominate the atmospheric observations to date. And that's just because they're very observable. And then for the rest of the talk, with that big picture in mind, I'm going to give you first a brief preview of the kind of observations we are getting in these atmospheres. And I'll start with, you'll see that most of the observations that I'll be showing you are for hot Jupiters. Okay, so for the purpose of this talk, because we are operating on a limited timeline here and there's a lot to cover, I will focus predominantly on transiting exoplanets. We are not going to talk much about direct imaging or about, I'll talk a little bit about how high resolution spectroscopy of radial velocity, i.e. non-transiting planets, can also be made. But for the most part, I'll stick to transiting planets for simplicity. Now, we all know what transiting planets are. So as the planet goes in front of the star, you can infer the atmospheric composition of the planet at the day-night terminator, at this limb, basically. And that's because when you're in transit, some of the starlight is coming through the atmosphere at the limb. And when you subtract that from the before transit stellar spectrum, you're left with what is the absorption spectrum of the planet's atmosphere. So that's just the transit depth, okay? The area of the planetary disk, or the area of the stellar disk, as a function of wavelength. So you can see in this example, this was obtained with the Hubble Space Telescope. You can see this huge water vapor absorption around 1.4 micron from that sort of geometry. And then when the planet goes behind the star, just before the planet disappears, you're seeing both the stellar and the planetary spectrum. And when the planet disappears behind the star, you see just the stellar spectrum. And if you take the difference of that and divide by the star spectrum alone, what you get is the planet's thermal emission plus reflection over the star. So this is the planet-star flux ratio you can get also as a function of wavelength. For thermal emission, it's just this, the area ratio times the ratio of the brightness of the planet or the star. And in between those two, you can also get the phase curves, both in the optical and thermal. In this particular case, it's the thermal phase curve you can get of the planet as well. So you can see there's a lot of information packed in the spectra. In one case, you're getting compositional information at the terminator, at the limb. In other case, you're getting thermal emission information, and everyone in between, you're getting longitudinal variation as well. So you can create brightness maps with those sorts of observations. Now, as great as these spectra are, and I'll show you even greater spectra, but I always like to be humble about the field in where we started just about 10-15 years ago. These were the first observations we were using to claim water vapor detections in these planets. Today we wouldn't claim these molecules from these sorts of photometric, just photometric data points. But that's all we had at that point. So fair enough, we did what we could. But it's always good to go back to where we were not so long ago, so we can tell when we see spectra like this, we can appreciate how good the data quality has been in recent years. Okay, so these are all Hubble spectra, and today getting spectra like this, look at these error bars. Today getting spectra like this for hot Jupiters is a pretty routine task, pretty routine. Now, if it seems so simple, I would like to draw your attention to these error bars here. They are few tenths of parts per million error bars. Okay, we are talking about few in few parts per 100,000 here in flux measurement. So these are extremely precise observations as a function of wavelength. So these are still very hard to hard measurements to make, but we have perfected the techniques that it's no longer impossible. It is pretty routine. So we have gone beyond now just measuring spectra. This is the first such high quality spectrum of a hot Jupiter was made only in 2013. That was only 8 years ago. But now in recent years, we have already moved on to population studies. You see already in 2016, there was the study of a population of these objects, all hot Jupiters, and you can see all the way from optical to infrared spectra for this population. We have already done this, and you can see good water features in a lot of these spectra. We have also done that, attempted that for hot Neptunes and super Earths, which are much smaller planets. And in a handful of them, we do see these sorts of bumps at the water features. So great. So for Neptunes also, we can measure water vapor features pretty reliably these days. But as you go down, this is basically going down in mass and radius as well as temperature. Okay, so by the time you hit GJ 1214, we are talking about planets about around 6 to 8 Earth masses, 5 to 8 Earth masses, and about 2.5 Earth radii. We're talking about here. So by that time, we until recently have seen only flat spectra. Okay, so we have attempted the precision is not the problem. We get like very high precision observations. It's just that the signal is much smaller. So those are high quality space-based observations. But I also want to say a few words about ground-based observations. So all these spectra have been obtained with 4 to 8 meter class telescopes from ground. Now today getting sodium detections like this is pretty routine again. Okay, so pretty routine. With 4 meter class telescopes, and also with 8. This was with the VLT. This was with the HARP spectrograph. This is also with an 8 meter class telescope, and so on. The sodium detections are pretty secure. Detections of other molecules, TiO and VO, are being revised, and so on. But nevertheless, the point to be made is that obtaining the precision required to make such detections is not a problem even from ground today. Okay, so we have been pretty successful over the past decade, I must say. So I've showed you only transmission spectra so far, and this is just one summary plot, plot of thermal emission spectra from this paper here. And this is to say that we are getting the high quality thermal emission observations also for a large number of hot Jupiters across the board. So I'll just summarize. So if you want to know more about the state of the art, you can read my review paper in Annual Reviews a couple of years ago. And the field is moving so fast that some of these plots need to be updated very soon. But you'll see that we are getting this quality of spectra for transmission spectra as well as emission spectra for a wide range of hot Jupiters. You can see the masses, okay, for all of these objects and temperatures. And at the end, I'll just show you one plot here where this is already from about 7 years ago, where phase resolved spectra have been obtained for a hot Jupiter. So you can actually create brightness temperature maps as a function of phase in the atmosphere, in the planet's orbit, and you can derive the spectra as well as the thermal profiles as the planet is going around the star. Now, this was done, as I said, 7 years ago, but this is a very expensive observation to make. This took about 60 HST orbits. For those of you who make space-based observations, you know that's a ton of time. Okay, so we can afford to make only a couple of these observations in several years. So there are a couple of such observations, but this is by far the best one in my knowledge. So I've showed you lots of observations, but let me just show you quickly what we do with such observations in terms of compositional measurements. And this is where atmospheric retrieval comes in, where you basically take your data, put an atmospheric model together, where the composition and temperature structure in the model atmosphere are free parameters, and then combine them in a parameter estimation scheme, and you can actually retrieve the composition and temperature structures of the planets, atmospheres. So we are going to have a discussion on methods later on. So I thought I would just put this slide saying that today conducting atmospheric retrieval is pretty routine. Okay, so I was involved in some of the first development of atmospheric retrieval techniques for exoplanets, but today, in just about a decade, we have about a dozen such codes in the field with different levels of complexities, of course, and different flavors. But this is to say that it's a very standard thing to do. If you have a spectrum today, the first thing you would do is an atmospheric retrieval, which was not true 10 years ago, where you would pick spectral features by eye in many cases. So the field has come a long way in that sense. So let me show you what those abundances look like. So these were the first measurements and of abundances here. So that's from my work in 2014 and several other collaborators from early on. But in recent years, we, especially in my group, have gone on to this ensemble abundance estimate. So you can see from this work in 2018, we have made measurements of a number of about 10 hot Jupiters in this case, and their water abundances. I'll show you a better plot with better abundance estimates in a second. So from these sorts of spectroscopic observations, now we are going to talking about metallicities as a function of planet mass. Okay, so this is again putting combination of transmission, thermal emission measurements, direct imaging measurements, and so on, and just giving you a summary, and you can read more in this paper. So one thing we have noticed across the board, the abundances are still the estimates have large error bars and so on. But one trend that is emerging already, which was already seen in the very first, as I said, in the very first work that I was involved in, where the abundances were pretty low. So recent more and more observations are just confirming that trend, that across the board, we are seeing that many of the hot Jupiters have subsolar water vapor abundances. There are a couple that do have supersolar abundances as well, but for the most part, we are seeing subsolar H2 abundances. And we don't have a good universal theory for why that is the case, but I think we also should be cautious and refine our observations more and more before we can confirm that that is in fact the reality and there is no observational bias and so on. But this was one of the most recent studies that we had done, where we are seeing that across the board, all the way from sub-Neptunes to hot Jupiters, we are seeing this blue curve here is a fit to the exoplanet data, water vapor abundances, and we are seeing that that abundance trend is lower than what we see in the solar system based on methane abundances. Okay, so but we don't see that for other metals like sodium and potassium, where we see actually some or more of them have super solar metallicities. As I said, so that was a very fast review on observations and abundance estimates for transmission spectroscopy. And I haven't done justice to the whole field because there's a lot going on in direct imaging, as well as high resolution spectroscopy for both transiting and non-transiting planets. So I just thought I would just put this slide on, saying that there are a number of studies out there which are detecting CO, water vapor, in some cases HCN, and so on, and a lot of metals actually in optical high resolution spectroscopy across the board. So I'm not going to spend too much time there, but I will say that even in high resolution spectroscopy, we have gone beyond just detecting species, and some pioneering studies, such as the studies listed here, are also beginning to combine the high resolution spectra with low resolution spectra and beginning to get precise abundance estimates. So you can see the error bars here. I'm not sure if like a 0.01, 03 error bars are really representative, but that's what we are seeing. So even if they're 0.1 dex error bars, that is still a huge improvement. Okay, so I'll summarize atmospheric inferences here, and the key finding is that we are detecting various molecules. A number of these objects have subsolar H2 abundances, and then we're also detecting clouds and hazes, thermal inversions, and so on, and we are seeing the beginnings of exoplanetary mass metallicity relations. So I've only come to about half my talk, and we have covered a lot about the big picture and exoplanetary atmospheric observations and abundance estimates. So in the remaining short time, I am going to talk about two emerging areas, briefly about planet formation, because that's a relatively old topic. And by old, I mean like we have been talking about it for 5 to 8-ish years, and I'll spend more time on the sub-Neptune regime. So when we're making these abundance estimates, a number of studies in recent years, I've listed in a lot of them here, are trying to sort of reverse engineer the formation origins of these planets based on their abundance estimates. And the reason for this is that for Jupiter, we see a number of elements are enhanced relative to solar. At that time, the H2 abundance, when Juno was about to go, and this was with the Galileo probe, the H2 abundance was not known. Okay, but now Juno measurements have obtained an H2 abundance, which we think straddles this boundary between 1 times solar to a couple of times solar, but the jury is still out on that. Now, when we go to exoplanets, the predictions has been that as you go in lower in mass, planet mass, your metallicity should increase. Okay, that's because smaller planets are more prone to accreting more solids and less hydrogen relatively, so you get more and more metallicity. So two predictions from core accretion models over the literature over time has been that you expect supersolar atmospheric metallicities in giant exoplanets because even for Jupiter you expect between 3 to 7 times, and you expect oxygen enhancement of this because you accrete more water in the solids relative to carbon and other species, so you expect subsolar C2O ratios. But as I said, that is not what we are seeing. We are seeing that the water is depleted relative to our expectations. So whereas that's not the case for the alkali metals and other metals. So this is still an emerging topic. I won't spend too much more time on this, but it's just to say that there are a number of theoretical studies that are ongoing, which are trying to relate atmospheric abundances to their formation mechanisms. And in parallel, there are also various studies that are trying to get more and more precise abundance estimates, and already we are seeing a problem, is that the oxygen abundances we see are not as abundant as we would expect them to be. Whether this is pointing to some fundamental difference in formation mechanism from what we expect in the solar system, or these are detection biases, is yet to be determined. Okay, so there is another subtlety, is that depending on your C2O ratio, I mentioned how the C2O ratio can also change in the disk. Your abundance, water abundance, can also change. So whether the low water abundances we are seeing is because of the low metallicity or because of a high C2O ratio, we still don't know yet. Okay. So there are various open questions. So I'll just leave this topic here with this nice plot from Oberg et al., who very early on showed that as you go far away in the disk, your gas in the disk will have higher C2O ratio relative to the solid. So if you accrete more gas from far, out from the outer disk, then you can actually have high C2O ratios in the disk and hence low water abundances. So there are a number of such studies happening in the literature. So we'll leave that topic there, okay, with this summary. So so there are various avenues for future studies on tying atmospheric compositions to their formation mechanisms. So that's the summary to take away. And there is no definitive results yet in the field, but it's a very happening area. And with JWST, we are going to look at these abundance estimates in much more detail. In the remaining time, what I'm going to focus on is the latest frontier of the field, which is the sub-Neptune regime, small planets. Why is it the new frontier? It's because very early on, the very first slide of my talk, I already said how sub-Neptunes dominate the exoplanet population. Okay? And even within that population in recent years, we have seen that there is a bimodal distribution of radii. Okay, so this is called the radius valley in the sub-Neptune regime from a number of these works. So just from the macroscopic properties, the masses and radii, they're already fundamental questions. The questions, for example, are these planets more like super Earths, as in like enhanced Earth-like compositions, but much bigger solid planets, or are these sub-Neptunes, which is take the mini Neptune-like internal structure, which is ices and rock and a hydrogen-rich atmosphere, and just preserve the structure but make it much smaller. So depending on whether they're super Earths, mostly rocky planets, or mini Neptunes, you can have very different atmospheric properties and physicochemical processes happening in the atmosphere. And similarly, what causes this radius valley in the sub-Neptune regime is also a big open question in the field right now. Okay, so there are fundamental questions to address there. But more from an atmospheric point of view, what makes this very exciting is that these planets are about the best bet for atmospheric characterization in the near future, as far as low mass, low temperature planets are concerned. It's because they're abundant in demographics and they're optimal for atmospheric characterization because of their puffier, potentially puffier envelopes if they have hydrogen-rich atmospheres, and which will also make them accessible in the temperate regime. The reason I say this is if you take an Earth-like planet around even an M dwarf, it's at the edge of observation with JWST, of observability with JWST. Maybe we can detect a chemical signature in an Earth-sized planet around an M dwarf. But if you just take the entire sub-Neptune regime between an Earth size, basically Earth radius and 4 Earth radius, there are tons of planets here which are very easy to observe with JWST. You can have low temperatures. You can even have 300 Kelvin temperatures and still observe them. And I'm going to give you an example of that in the remaining slides. So this is a case in point, a mini Neptune called K218b. So the mass of the planet is around 8 Earth masses, and the radius, the latest, this was an old radius estimate, but the radius estimate today is around 2.5, 2.6 Earth radii. Okay. The important bit is that the equilibrium temperature of the planet is about 300 Kelvin or lower, depending on what you assume for the albedo, which means it's in the habitable zone of its host star. These temperatures are habitable. even though the planet is significantly bigger. So even with HST, although it took 9 HST visits, you can see that water vapor was detected in this atmosphere in these 2 studies a couple of years ago. And we went ahead and also did an atmospheric retrieval, as did the other studies. And indeed, we confirmed that you can detect water very confidently in this atmosphere, but you have only upper limits on the other compounds like methane and ammonia. So that's great, right? So already with HST, we can detect the atmosphere and water vapor in the atmosphere of a sub-Neptune planet in the habitable zone of its host star. No one, even 5 years ago, would have dreamt of this result today, which also says that this is trivial to do with JWST, okay, if you can already do it with HST. So we've talked about interior composition, atmospheric composition, but what you can also do is take these abundances and impose them as boundary conditions for your internal structure model. The top layer of your internal structure is basically the atmosphere. So you can use those abundance constraints as boundary conditions for the atmosphere and put constraints on the interior composition of the planet. Okay, so in this study, we put constraints on the core mass fraction, the hydrogen helium envelope mass fraction, and water fraction, and so on. And what we demonstrated here is basically a wide range of scenarios can explain the mass and radius of the planet. So there is no unique solution. But what is interesting is a subset of these solutions. I'll take you to this plot to demonstrate that this is the first time where we combined an atmospheric and an interior model together, and tried to put constraints on the boundary, conditions at the boundary of the atmosphere and interior. So using the combination of atmospheric and composition and the bulk properties. And then what we showed that even though a large number of solutions can explain those observations, a subset of solutions, this is just showing the water phase diagram at that boundary, at the atmosphere interior boundary. You can see liquid phase, solid, supercritical, and so on. And this is just the temperature and pressure, the loci of the temperature pressure at that boundary. And you can see that a subset of these solutions lie in the liquid phase of water. Okay? So this by no means guarantees that this is a water world or there is actually an ocean underneath, but what it does say that there are solutions that can allow for water underneath a hydrogen-rich atmosphere at habitable conditions in the planet. Okay, so that's exciting. It's not definitive, but it's exciting. So what that also allowed us to do is to enter into this new regime of modeling where we are beginning to combine atmosphere and internal structure of model internal structures of planets to put constraints using atmospheric observations and their bulk properties. This is an interesting study with my student, Anjali Piet, where we explored a wide range of atmospheric properties, atmospheric temperature profiles, and showed that indeed for a wide range of haze abundances, cloud compositions, and so on, you could get ocean layers at the bottom of the atmosphere. So this is exciting direction. So this is what I'm talking about as a future for the modeling of sub-Neptune regime, where you have these observations, you have from those you can derive the atmospheric conditions, and from those you can put constraints on your interior conditions using coupled models of atmospheres and interiors. So there are various things you can do with it, with those sorts of approaches. These are some future directions for sub-Neptunes. You can study mass-metallicity relations, you can study atmosphere interior coupled constraints to resolve big questions like super Earths versus mini Neptunes. You can also study chemical disequilibrium processes, and you can also study constraints on planetary habitability. So I will stop here and ask our hosts about how much. I think I'm almost out of time, but depending on how much time you want to allow, I can talk about a little bit more about one or more of these topics if you're interested.
I think at the level of 5 minutes or so, there is flexibility. Yeah.
Okay, so let's go for 5 minutes. And what I had planned, there's a lot of content here, so I'll just plan to talk about the bottom two. Okay, I'll cover that in 5 minutes. So I'll talk about two very frontier of the frontier topics in this domain. So first we'll talk about chemical disequilibrium. So this is a plot showing chemical equilibrium in temperate atmospheres. It's a complicated looking plot, but it's we'll just focus on carbon monoxide and methane here. Okay, just look at the black and blue curves. As a function of temperature, for a solar abundance elemental composition, you will see that as temperature increases, methane decreases, CO increases. That's it. That's all you need to know. So in chemical equilibrium, that is what you would expect. That is why low temperature atmospheres in the solar system, like Jupiter and Neptune, have a lot of methane and not much CO, whereas in hot Jupiters, you don't see much CO at all. But when it comes to temperate mini Neptunes, what you expect then, by temperate, we mean all below 700, 800 Kelvin temperatures. So you expect a lot of methane to be present and not much CO. However, you can get a little bit of CO by what is known as vertical mixing. I hinted at it before, where you could have from the lower part of the atmosphere, which is hotter and you can have more CO, you can dredge up some of that CO depending on how strong your mixing is. So that is called vertical mixing, and it's a very non-equilibrium phenomenon, and that is what is used to explain some of the CO seen in Jupiter as well. Okay. So some of the first evidence for such processes in exoplanets happened almost exactly a decade ago in these studies for a Neptune GJ436b, which is around 600, 700 Kelvin temperatures. And we didn't detect methane, but we did claim a detection of CO, which is exactly opposite to what you would expect in chemical equilibrium. So that was an inference of a non-equilibrium chemistry. So that's what this is showing, CO detection here and no methane detection in other wavelengths. So today, this is a nice plot which shows that there are many sub-Neptunes below 600 Kelvin where you expect a lot of methane but not much CO. Okay, low temperature atmospheres and low mass atmospheres. So that is just vertical mixing, but you can also have a lot of photochemical effects in these atmospheres. You can see a ton of new species like HCN and C2H2 can also be produced, and methane and ammonia can be depleted depending on what sort of surfaces you have. At the bottom, you can deplete some of these species and increase some of the species. Bottom line, you'll have these slides later, but bottom line is that you can get a lot of deviation from chemical equilibrium when you have non-equilibrium processes going on. So I already mentioned to you earlier that we don't detect methane in K218b, but there are some claims to the contrary by this paper, which need to be checked. But this is typical of what is known as the missing methane problem in temperate exoplanetary atmospheres, which is across the board. We have looked at several planets now as a field, about 3 to 4, maybe even 5 planets below 600 Kelvin equilibrium temperatures, and we have never actually found methane. And that's a big question in the field. Why are we not seeing methane? Is there some strong chemical disequilibrium process that's happening in these atmospheres? And this sort of thing is very easy to study with JWST. So you can see the constraints. This is for a typical sub-Neptune spectrum, and we can see that you can get constraints of 0.1 dex precision on all these compounds, so you can easily detect chemical disequilibrium in these atmospheres. So in 2 minutes, I'll also touch upon planetary habitability. As I said, for K218b, we are beginning to see some solutions which are possibly habitable, which make these planets possibly habitable. Just a couple of weeks ago, actually, we published this paper where we explore the full range of planet properties between their masses, radii, equilibrium temperatures, and so on, which can allow for similar habitable solutions as K218b. And what we deduced is that you can actually have planets all the way up to 500 Kelvin equilibrium temperatures and still have liquid water surfaces below their hydrogen-rich atmospheres. That also means that you can have planets as large as about 2.6 Earth radii at 10 Earth masses and still be habitable if they are below those equilibrium temperatures. And that also depends on their host stars. Especially for M dwarfs, they're very good for habitability. What this revises is that we have this as the classical habitable zone that we all know from various numerous studies. But if you consider these sorts of planets, we call them Haitian planets, large planets around M dwarfs, we can go all the way up to 500 Kelvin. As I said, in this case, it's for day and night side habitability, you can go up to 430 Kelvin and still have habitability. And what that does is that if that's the terrestrial habitable zone, you expand that enormously. Okay, so that whole cyan and red and purple regions are habitable in one way or other. So that remarkably changes the space of planets that we can observe that can be habitable, basically. So I'll leave these slides, you can read this paper, but we talk about different kinds of habitability, planets which are habitable around the surface or just on the day side or just on the, just on the night side, or planets that are extremely cold, very far from the star where they have very little radiation, but they can still be habitable. They can still have water interiors. So yeah, so planets can be much bigger, much hotter, and still be habitable under certain conditions we discuss in the paper. But most importantly, these are also planets extremely observable with JWST. This is with K218b, as I promised, as I showed you earlier. Here I'm showing you what the JWST constraints would be like for K218b. And you see that for all these prominent molecules, you can get like 2-3 dex precision in water, methane, ammonia, but in also the biomarkers, you can get very good precision and you could potentially detect them. So, so that's the summary, is that with JWST, the future is extremely bright in that we can get very good abundance constraints for all these interesting sub-Neptunes, and we can answer all these various questions that I covered in my talk, okay? So I'll leave you with this last slide, is that the future of exoplanet science currently looks extremely bright. In terms of planet detection, there are various missions that are happening or about to come in this decade to detect the small planets, sub-Neptune planets around low mass stars. And at the same time, there are also numerous facilities focused on atmospheric characterization of these objects. JWST, if all goes well, hopefully will start operating by next year. And then we also have the ELTs coming up, and obviously Ariel coming on a longer time scale. But all this means that, in my view, this decade is likely going to be the golden age of exoplanetary science, where we can expect some big breakthroughs coming. Thank you.
Thank you so much, Madhu. Beautiful talk. I think you conveyed quite nicely how exciting it's been the last 10, 15 years, and even more exciting the coming decade. So questions now. Anyone please wishing to ask a question, just you can either express say so in the chat, and they can formulate the questions themselves, or type the question and then I repeat it.
Carlos, I can ask a question if you wish.
Please, go ahead.
Nikku, Madhu, great talk. I didn't see too much of a connection with the stars and the stellar composition, except for the radius gap, where the star comes in as a better characterization of the planet radius. What's your view on this connection of higher metallicity and having higher metallicity, not oxygen rich,
Yeah.
where is the domain for the hot Jupiters?
Yeah. Now that's an excellent question. So in the past, when I used to give talks, I would have a big section discussing why stars, the stellar composition is important for that connection. Because whenever we are talking, I didn't cover a lot of planet formation, I just touched upon it. But whenever we are talking about connecting the atmospheric composition of a giant planet with its formation mechanism, the underlying assumption is that the primordial composition of the disk is the same as that of the star. So when we are talking about these elemental enhancements, they're always relative to their host stars. So in one plot, I showed this mass metallicity plot from our recent survey. All the abundances, the water vapor abundances, which we use as proxy for the oxygen abundance, are relative to their host star oxygen abundances. So they're not all relative to solar, they're relative to their own host star abundances. So the star is absolutely critical in that sense, is that we definitely need the stellar abundances to normalize the planetary abundances. And only then can you make that connection. but that's only one from a scientific perspective, but there is also another very important aspect, which is when we do this transit spectroscopy also in determining the spectra, it's very important to make sure that you're not seeing contributions from star spots in the observed transmission spectra as well. So again, that's a whole different topic where today, even like we have developed the retrieval tools where you retrieve the stellar heterogeneities and the planetary properties simultaneously. You would have to do that, otherwise some of the stellar heterogeneities can mimic the features you're seeing in the transmission spectrum of the planet. So there are multiple ways in which the star is extremely important, but I didn't have time to cover that particular aspect here.
Thank you.
One question that pops to my mind is also the fact that, as you pointed out at the very beginning, these atmospheres are quite complex, right? You have circulation, you have photochemistry, non-equilibrium chemistry. In the end, how reliable or how sure can one be that the retrievals are unique? And you know, the obvious thing that could be done would be try one, you know, Venus or Mercury are transiting the sun, right? Has this experiment been done to check, you know, whether the measurements from the retrievals fit what is being measured by probes in these planets?
No, that's a very important question, actually, very serious question. It's a matter of the precision and the specific species you're focusing on. So if you look at Jupiter, abundances of Jupiter solar system planets, the precisions you're talking about there are order 0.1 dex. Depends on what species you're looking at. If you're looking at methane, which is very abundant in these atmospheres, we're talking about precisions of order 0.few dex, 0.2, 0.3 dex. That is not the precision at which we are looking at those particular species in exoplanets. The only molecule that we can detect reliably, robustly in exoplanetary atmospheres has been water so far. And even for that, most of the time we are detecting abundances. The best one I've seen is of the order 0.5 dex. Okay? So at that level, sure, even that we may not be very confident. Maybe at 1 dex level error is a reasonable uncertainty. But at that level, a lot of the other effects you're talking about, you know, be it photochemistry, dynamics, this and all, sort of like get marginalized over. In the sense that however you change your photochemistry, dynamics, and so on, you're not going to change your water abundance by more than a dex or a few for a certain atmosphere at a certain temperature. There are exceptions, of course. If you go to very hot atmospheres, highly radiated atmospheres like 2000 Kelvin or higher, then you can have dissociation of water as well. So again, then they become less reliable. So what I'm trying to get at here is that there is a subset of planetary parameters and a subset of molecules where it is very reliable to make estimates. On the other hand, there are a lot of other things which are not very reliable at all. So if you told me, see, as I already mentioned, you can't even detect methane, let alone getting a precise abundance estimate. So I hope I answered your question in that it depends on what property you're looking at. You can't generalize and say across the board we'll make precise detections on all species. You can say that for the most dominant species, we could make a reliable abundance estimate to a certain level of precision.
Thanks very much. I see Charles Cowan.
Yes, for the point of view of those of us who have a background in stellar spectroscopy, the task that we have as far as exoplanet science goes is trying to use the stellar compositions as an indication of the planetary compositions. And the diversity of planetary compositions and forms just seems huge to me compared to the diversity of abundances of, say, solar-type stars. Nevertheless, some progress has been made with the possibility of an engulfment of a planet changing the composition of the star. And I just wondered if you would be willing to comment on where this problem looks to you. Is it promising to be able to use the stellar composition to say something about the planetary composition, or does it just look too formidable?
Yeah, no, that's a very interesting question. Actually, I've spent the last decade thinking about this particular question for a very specific reason. Planets, by definition, are expected to be much more chemically diverse than stars, because in planets, most of the time we measure molecules. If you're measuring atomic elements and atomic abundances, that's a different matter. But you're measuring molecules in planets, and molecules have a much more sensitive dependence on a wide range of processes, both on their elemental compositions and elemental abundance ratios, but also on the physical and chemical process happening within the atmospheres themselves. And that is why you're seeing this wide, or you expect this wide diversity. For example, if you can have the same elemental abundance of carbon and oxygen in a planet, but just place it at different distances from the star and making it two different equilibrium temperatures, let's say between 500 and 1500 Kelvin, and they'll have very different compositional makeup in terms of the molecules. So in that way, it is justified to see a wider chemical diversity in planets than in stars. But then the question is, what can we do to use the star to understand about the planet? And that is where, there are some stellar abundances that are more important than others. For example, the carbon to oxygen ratio or the magnesium to silicate ratios can have a big impact on the mineral compositions of planets. For example, there have been various studies that show that, if you have a magnesium to silicon ratio spanning, across the border of 1 with, let's say from 0.8 to 1.2, that can give you very different rock compositions that go into forming rocky planets. Same for the carbon to oxygen ratio, the boundary there is around 0.8. So if you have C2 ratios below 0.8 or C2 ratios above 0.8, that can give you a spread in planetary mineral compositions again. So that is one avenue where elemental ratios can inform what sort of diversity you expect in planetary interior compositions. The other place where it matters is, as I just mentioned, is the metallicities of the stars themselves can have a big impact on the planetary atmospheric metallicity, and that feeds into other atmospheric molecular compositions as well.
Thank you.
All right, thanks very much. To finalize, we would like to have a bit of a discussion about resources available for students and researchers who start in this field. So Daniela, you would like to lead the discussion?
Okay, thank you. So we would like to use this platform also to discuss the current problems, because a lot of problems can be solved relatively quickly and easily. And for example, what I see at our university is that we have now a generation of students that grown up in the time of discoveries of exoplanets. And they really came and really would like to work on this field. But the problem is that we can offer. I already included some chapter about exoplanetary atmospheres in my lectures, but as I don't work in this field, so it's of course not sufficient. So I guess that a lot of universities is maybe in the same situation. Therefore, sorry, I would like to ask Nikku if you can help these students if you know about some good lectures if somebody can help these students and take them for bachelor or master thesis or something, really something to help this generation, because these students would like to work in this field, but it's a problem how to start.
Yeah, so there are several summer workshops that happen across the board in various institutions do that, summer workshops in exoplanets. Sometimes they're not always on atmospheres necessarily, but sometimes they're on atmospheres, and that is usually a good forum for students to get involved in like a quick summer project, and then they gain the experience and the contacts to develop further. So that's one easy way to access. I mean, there are master's programs, some universities more than others specializing in exoplanetary. I mean, where a university has a good exoplanetary atmospheres expertise, that is obviously a good venue for masters in that program. But I don't think there is a universal, like that, there is a program specifically on atmospheric, on exoplanet atmospheres master's program. So that I think is going to be a difficult avenue. You just have to focus on researchers who work in that area and go on a case-by-case basis. But I think the summer programs are a better venue to train students quickly. And then there are lots of codes available online, for all these things. Today, for exoplanet atmospheres, you have forward modeling codes, where you can generate transmission spectra, emission spectra, whatever you want. You could do, there are a number of retrieval codes that I showed a slide on, are also publicly available. So students can download them and test them. The JWST observation simulators are also publicly available. So there is a lot of resources out there that students can already use and at least do some test cases, and then once they have gained a certain level of expertise, then they would have to contact people in that research area and get real projects. But at least to get them started should not be a bottleneck, given the public codes available.
Thanks. Okay. And do you think, or somebody, that there is a possibility for these students to join some university course, because maybe still this semester will be online? So is it possible to join some courses, or is it everything, private or closed only for students?
I have to admit, I'm unaware of a completely open source course focused on exoplanetary atmospheres. I'm sure there are courses on exoplanets in general that are open source, open courses. But as far as I know, I must say I'm unaware of a course specifically on exoplanetary atmospheres that is totally open courseware. But there are public platforms, simulation platforms, where the codes are available, and the developing groups might even be able to support the students who want to train on those courses, on those codes.
Okay, thank you very much. So I hope that this helps students, and they will start to learn something.
Yeah. But this is, I think this is something that that can be discussed with experts, right? And we can discuss this after at a later stage. But I mean, there may be experts willing to offer short-term projects on an ad hoc basis. I just don't know about it. So that is something that can definitely be explored, and there could be a common platform for students to get up to speed in a given area. I see a raised hand. Is that from before or?
Yes, but
Yes, Charles. I think it's from before.
maybe old one.
We had a discussion for some years now that one of the things that the G5 Commission could do was to group resources, organize resources, and make them available to our community on the IAU web pages or
Right.
an annex, right?
Yeah.
I think that initiative, it requires some muscle, but it's a very good idea for both planet and stellar atmospheres, and it would be very interesting to have such a repository.
Yeah, no, if the commission would like to have a team which is interested in doing that, I would definitely be willing to provide inputs and give the right information and ideas. Just contribute to the discussions along those lines.
Okay.
And I'm sure there are others in the field who would be happy to do so as well. We all want to help students at the end of the day. It is, it's just that one person cannot do it. Some organization or commission has to form a small team which can focus on things like that and make it happen. But I'm sure a number of experts, I run other sort of think tank style programs, symposia and so on. And people in the field are generally willing to help young people. And that's why there are so many open source codes as well. So people want other people to use them. But you still need someone responsible to curate the whole thing. And I think that is where the commission would help a lot.
Absolutely. Well, I think we're a bit over the hour, almost 10 minutes. Maybe it's a good time to stop here if there are no other further questions or.
Oh, somebody, wait. Okay. It's maybe.
Okay.
Thank you.
Thanks, everyone. See you next time.
Thank you so much. Thanks so much, Madhu.